true. All right, great. Thank you all for being here. This morning, I'm going to talk about some of my work that I've been doing here at SESYNC. So a lot of this material is new for me to be presenting, and some of it is still a little preliminary. I'm going to be talking about 2 case studies on looking at local and then global consequences of environmental shocks. I'll start off by providing some background about why I focus on seafood to look at these kinds of shocks, some of the concepts around resilience and thinking about resilience within food systems, and then I'll present work that I've done on, this is already published work on looking at shocks to national seafood supply and trade. And that really motivates my work for then digging in a little bit deeper at some of the local consequences and global consequences of shock events, specifically looking in section 3 on the impacts of a cyclone on small-scale fisheries in Madagascar, and then some of the global consequences of a red tide event to salmon trade in Chile. So start off with some background. So why do I think about seafood as the system of focus for looking at these environmental shock events? First of all, seafood is one of the most highly traded food commodities. It's become increasingly globalized and has in fact surpassed many of the other kinds of crops that we think of as being highly traded, like rice and cocoa and coffee. All of those combined, actually, it's more highly traded. Second of all, it's really important in food security. It provides around 20% of global animal protein consumption and is an important source of micronutrients as well as essential fatty acids. Then the final part is that it interacts really directly with the environment. So our capture fisheries, we take seafood straight out of the ocean. And then for aquaculture, we rely on a lot of environmental resources as inputs in terms of the water resources, the lands, as well as energy to produce that aquaculture. Because of this, there are a lot of entry points along the supply chain of producing seafood where different kinds of environmental disruptions could occur and create this sudden decrease in seafood production. So I think that makes it a really interesting system to study these kinds of shock events. Now, I periodically talk about my work in relation to sustainability, resilience, and food security. And since these are all pretty big buzzwords, I'm going to go really briefly about what I mean when I say them, as well as their relationship between each other. I'm not talking too much about sustainability today, but typically when I do, I'm really referring to sustainability in the sustainable development context. So how are we meeting fundamental human needs while preserving life support systems of the planet? So preserving the different kinds of environmental services into the future. I talk a lot more about resilience, though, and some of this resilience has historically fallen within the sustainability science literature. Resilience I think of as the capacity of a system to absorb disturbance while undergoing change to retain essentially the same function, structure, and feedbacks. And I'm going to look or talk about resilience and where it comes from a little bit more in a moment. So I'll move on to food security, which is a situation when people at all times have physical, economic access to safe and nutritious food to maintain a healthy life. This has been looked at in terms of 4 pillars of food security. So that's thought of as availability, so that there's enough food physically available for people. Access, that people have physical and economic access to those food resources. Utilization, that they're healthy enough so they don't have some kind of parasite that prevents them from actually being able to utilize those nutrients. And then stability. And stability means that they have availability, access over time, and that ties into this idea of resilience, so that if there are different kinds of disruptions, people still have access to that food. So resilience and food security, these 2 ideas go together quite well in terms of thinking about how these food systems can respond and adapt to different kinds of perturbations. A lot of people who've been looking at social ecological resilience think about it with its basis in ecological resilience literature, which all kind of comes around this commonly depicted ball and cup model, where you have some kind of stable point where along this x-axis in the food world you may have less food secure and more food secure. And the basic idea is that there's some kinds of feedbacks within that system that might maintain this particular state, such that if there's some kind of perturbation, the ball stays within that little dip and doesn't get tipped over into this more food insecure state. That doesn't necessarily mean that you couldn't have some kind of large perturbations that might push the ball over that threshold and put people into food insecurity. And you can also have changes to this underlying system, so this underlying landscape, such that that same small perturbation might now be able to push people into the food insecure state. And so it's really by studying shocks that we can start to explore what the shape of this landscape is by seeing what kinds of perturbations might move the ball over those, over that hump into food insecurity, and what kinds of features might actually contribute to the feedbacks that maintain a system, so a food system within one kind of basin. One important thing to note, though, is that resilience is not always good. It's not inherently good. So you could have this underlying landscape keeping the ball in this particular area such that it's really hard through policy or other kinds of interventions to push it over into a higher state of food security. A common example of this is poverty traps. So there are features of poverty that maintain you staying in a less desirable state and make it really hard to escape that poverty trap. Now, this is a visual depiction of the underpinnings of a lot of the resilience literature. But one thing is that it's hard to do empirically, and so we, in terms of getting all of the models that actually build up that, so we use these shock events to explore the underlying shape and understand how it might be changing with environmental change. Another aspect of resilience is that anytime you are talking to someone about it, it's really good to get clarification on resilience of what to what. So you can have general or specific resilience, and it can be general or specific in terms of the outcome or the type of shock you're talking about. So just to give some examples of this, you could have a specific outcome, nutritional status, or even more specific kilocalorie intake on your x-axis, and you could look at how that is or is not resilient to a specific shock like a drought or to any shock more generally. In contrast, you could have a much more general well-being kind of variable and think about its resilience to a specific shock or to any shock in general. So this corner down here being the most general kind of resilience, where you're just thinking about general well-being and its resilience to anything that could kind of happen to them. So that makes it kind of hard, I think, to evaluate. And so I try to think about the much more specific outcomes, either in terms of nutritional status or something like kilocalorie intake or different micronutrient intake. My work right now takes primarily these specific shock events, but looks across shocks to try to get at a more general understanding of how these particular outcomes respond to shocks more generally. So this whole picture here, though, of this idea of a ball staying in this dip means that we think there is some kind of equilibrium state that exists. We think there is some stable point around which the ball is returning to. And I think that it could be possible that this does exist for food systems. There is some minimum amount of kilocalories, so some minimum amount of energy you need to intake to be productive and live and work, and that could create some kind of stable point. But if it does exist, it's probably really hard to identify actually what it is. So I've been looking into some kinds of alternatives to this equilibrium-based approach, and one of which comes from recently in a paper from attributes of the time series itself. And so I'm not necessarily going to be advocating for this, but this is one of the approaches that I've been starting to consider. This alternative views resilience as the ability of a time series to disassociate from its present and past time increments. So this is essentially using autocorrelation. And then they decide that resilience should mean that your state is not worsening, so they look at trend. So they define resilience as a function of persistence and trend. And then they say you have to also understand how likely it is for them to experience these perturbations. So they take into account the resistance of the system, which they look at as volatility and trend. So there are these other kinds of ways of thinking about resilience that are starting to pop up that are challenging this idea that you have to have this stability point, the stable point within the system, and that you have to, in fact, identify it. And so I think that's an interesting area when you're thinking about something as complex, maybe ill-defined within food systems. So I'll move on now, though, to some of the work that I've published on actually identifying shock events and understanding what happens to food supply and seafood trade at the national level. And the first step to doing this was to define what is meant by a shock. So I've mentioned my primary interest is really in environmental shocks, but from a more general view, shocks can arise from all kinds of reasons. So that could come from natural disasters or natural hazards like droughts or cyclones. There are environmental stressors like overfishing or an oil spill, as well as political and economic kinds of shocks like war, policy changes, or economic crises. Broadly speaking, though, when I talk about a shock, I mean some kind of sudden decrease in fishery catch or exports such that the producers can't respond to that drop within the time frame I'm thinking about. And so they're sort of in this short-term disequilibrium state. Now, that's a really broad conception, and so when I wanted to be able to look at this quantitatively, I looked at other systems and how they've defined shock events. Previous definitions that have looked at kinds of shocks have tended to be system-specific. So in drought, you have an index of the drought related to the soil moisture. Others require long time series, like flooding. So you have these long time series of floods, and you can look at what extreme events are within that history. Or they might be based on collective reports. So everyone just agrees this thing is a shock event. Each of these has a problem for applying it to the seafood context. So since we're talking about lots of different kinds of shocks, it can't be too system specific. There are not long enough time series to take that approach. And if it's based on collective reports, there could be bias toward identifying a shock if it's happened too long ago, such that there's not good reporting, or it happened in a part of the world where there just isn't very wide reporting that would get back to our databases. So I wanted to develop a statistical approach that could avoid some of this geographical and temporal bias. To appreciate what this statistical approach has to do, I'm going to show a couple time series that are from the data set. So the first thing it has to do is be able to deal with different y-axes. So you may have an overall similar kind of pattern in two time series, but with really different y-axes. You could have differences in trends. So this one is relatively flat, whereas this trend is increasing. And you could also have different levels of variability. So this is not a very variable time series. Both are increasing, but this one has high variability. And one thing in particular about this last one is that I did not want the approach to pick out every single dip in a highly variable system as a shock, because if these kinds of big drops or dramatic drops are happening frequently, they're not really unexpected in that sense. It's just a highly variable system. The approach that I developed is modified out of spatial statistics, and what it does is I first fit a lowest curve and calculate the residuals off of it. And so what this lowest curve does is it essentially integrates some of the intermediate patterns or intermediate trends within the time series, so it's a localized smoother. And then by calculating the residuals off of it, I can look at the autocorrelation in those residuals. So the residual at one time step versus the previous gives you how big of a jump is there from one time step to the next. So if there's a really big jump, then that point is going to fall high off the line. So for example, this point. And in order to identify those ones falling really far off the line, I used an extreme value identifier, Cook's D. And so this is used in regression pretty commonly for identifying extreme values. And you see the spike here in Cook's D corresponding to that initial drop in that time series. I then applied this method for identifying shock points to the production time series for seafood. So this is catch and aquaculture data all together for each country, and identified a set of these shock points. Now, having when and where these shocks happened doesn't necessarily get at the cause of those shocks, though. So to do that, I did a systematic literature and news report search to identify the causes of those shocks, or rather, what others identified as the cause of these shocks, and in order to provide some context of what actually happened in these cases. Now, one question you can ask with this set of shocks is, are these shocks increasing? And the answer is really not really. So there's a huge range in magnitude of these shocks. So this is a log scale. And there's no real trend here over time. And another thing to note is that when you look by color of the cause of those shocks, the shocks occur for a variety of reasons. And so one thing to take away from this is really just that over space and time, these shocks are a relatively common feature of these seafood production systems. Now, to dig into those a bit more, though, and what actually happened in those cases, I pulled data on the change in imports, change in exports, and change in per capita supply. What you would expect to happen if there's less seafood being produced in one place is that the country would do some combination of increasing their imports, decreasing their exports, or decreasing their supply, where supply is production and imports minus exports and waste over population, to just make it per capita there. And what I found was that there were increases more often than decreases in imports. Exports, it was split about evenly, and supply more often decreased than increased. But the specific combination of these changes in trade and supply were really context dependent, and some of the cases where it seems a little counterintuitive can be explained when you dig into the specifics of what happened during that particular event. And I'll go into that a little bit more by looking at two shock cases that I identified. One's a political shock, one's an environmental shock. The data presented are the production data in black, imports in green, supply in blue, and exports in red. The shock point that was detected will be indicated by a vertical line. The first and largest shock that I found within the database was with the former Soviet Union in 1991. And I'm sure, as you guys can all probably guess what happened there, that's the breakup of the Soviet Union. So before the Soviet Union dissolved, they were highly subsidizing their fisheries. And when they broke up, about 80 to 85% of those fishing ventures filed for bankruptcy. The gear was split among the newly formed countries, and consequently, a lot of that production dropped dramatically. At the same time, the supply dropped dramatically, and you'll see at the exact time point, there's a decrease in both imports and exports, and then shortly thereafter, both imports and exports increase. Now, the supply behavior makes a lot of sense, but the trade behavior doesn't necessarily make sense with what you'd expect with this big of a drop in production, except for the fact that, of course, at this point in time, there was political chaos, and following that is when the Soviet Union opened to trade in the West. So it really requires looking at what was going on here to understand why this doesn't necessarily fit with what we'd expect on the trade side of the story. To turn our attention now, the next case, Sri Lanka, one of the cases, or the shock was identified in 2005, and this drop in production can be attributed to the tsunami event that occurred in December of 2004, which severely affected Sri Lanka and Sri Lanka's fisheries. Much of the production within Sri Lanka is small-scaled and for domestic consumption, but there is a big industrial fleet. The industrial fisheries were not heavily impacted by the tsunami, and you can kind of see that the imports and exports that are much associated with that were also not very affected by the shock event. However, one thing that is really interesting in this time series is that it recovers really fast. And in fact, production and supply far exceed what they did before the tsunami event. And this really quick recovery is not necessarily attributable to some sort of particular resilience of the fisheries industry, but rather to many foreign aid organizations that came in and handed out a lot of fishing gear, and in fact increased the fishing capacity within Sri Lanka to levels higher than they were before the tsunami. This has been a concern to some folks because people were already saying that there were problems of overfishing before the tsunami event, and so with all this extra gear and high catch, that has raised some concerns. But I think that particular behavior is a really interesting piece to the story that does not come to light without some of that additional context of the data. So when you take this picture all together, though, and there are these cases where there were changes in imports and exports, it implies that you have more distant impacts within the trade network. So if one country's importing more or exporting less, what's happening along the rest of those trade routes or trade paths? And then the second piece is that these changes in per capita supply are just at the national level. And this implies that there are changes for how much seafood is actually available and what people are eating at the subnational level, and it implies that there may be impacts on food security, but really doesn't get at it just by looking at that national scale. So we'll next dig into some of these subnational impacts by looking at a case on the local consequences of a cyclone on small-scale fisheries and what people are actually consuming there. People have historically tried to understand some of these local impacts of a shock and what the resilience of these fisheries are by doing some post-disaster analysis. And in these cases, they essentially see that some event happens, go in after the fact, and then try to understand what things were before and how they responded. Another approach is that people have been developing these kinds of indicators about the fisheries, about the resilience of fisheries livelihoods, or the ability of people to adapt to environmental change within the context of fisheries. And these are really index-based approaches. So this ties in some to what Eric Tate was talking about last week in the case of some of the vulnerability indices. This is a similar story that's going on where you have these composite indices, and they're really not empirically tested, these particular ones. This is empirical work, but we don't really have a before state for many of these cases, so it's hard to say what's actually going on and how much of it can be attributed to the event and which features enabled certain sectors or sections of the community to be able to rebound faster than others. So the event that I'm going to be looking at is some of the local impacts of Cyclone Enawo. So this is a cyclone that hit Madagascar in March of 2017, so this was last year. It was a Category 4 cyclone with maximum speeds of 144 miles per hour. It was the largest cyclone to make landfall in Madagascar in over a decade. It resulted in over 81 deaths and the loss of around 250,000 homes throughout Madagascar. And so this was a pretty devastating cyclone, and it actually hit pretty directly onto these 3 sites that my mentor, Chris Golden, has been conducting field work in. So these 5 sites along Antanjil Bay. The data that Chris has been and his team has been collecting in partnership with folks on the ground, there's decades of reef survey data, so there's quite a bit of ecological data that exists. I haven't worked with this data yet, so I'm still waiting to get some of that, but I have started looking at some of the socioeconomic data that Chris's team has been collecting really regularly. So here's a table of the data collection, but it ranges from dietary intake, including specific dietary intake about seafood. There's food observations, there's socioeconomic variables and what livelihoods people are participating in. There's bi-weekly per catch per unit effort data for fishing, as well as other kinds of natural resource use. In addition to this regular data collection following the cyclone, we were able to ask the team that was working there on the ground to collect additional data on some of the specific impacts of the cyclone, including doing a coping strategy index survey. The sites that we're looking at, this map's really not that useful. I was just extremely excited about making these icons on the map. So Kelly was helping me do some mapping. And these are a few of the sites. We do have so across these five communities, there are 225 households and 120 fields. So we have the GPS locations for where people are growing their different crops, which is important to relate back to some of the flooding data, since with the cyclone came a lot of flooding of these fields. So the questions for this project really more broadly are that we're trying to understand the impacts of the cyclone on fishing capacity and fishing catch, and understanding what some of the changes in fishing strategies are following the cyclone. Second is trying to understand the magnitude of the combined impacts of income generation and dietary intake on nutrition in that short versus long term, since we do have this long time series that extends before and after the cyclone event. And then finally, to get back to this question about resilience, I'm trying to understand whether some of these features and indices that people have been creating around resilience actually correspond to faster recovery trajectories and lower impacts within these systems. So the results I'm showing don't quite get at answering these questions yet, but do give some hints to what's going on. So I'm going to show a little bit of the data, but how we're envisioning how the cyclone would end up affecting nutrition is that it can disrupt ecology through the destruction of some of the reef structures, as well as direct impacts on some of the fish. It can destroy some of the fishing gear, and it also destroys property and different assets, as well as floods these fields and ruins the crops being produced on land. The ecological and fishing components come together and can shift catch, and then the catch and crops and property all sort of come together to affect what income people have to buy their other food sources. So this food available as well as income we envision come together to affect what people are actually eating within these communities. On the ecological side, as I mentioned, I don't have the ecological data yet, but the surveys that we did immediately after, there were wide reports of a lot of dead fish washed up on shore, so that does indicate at least some of these direct impacts. So that part's really just too soon to show too much yet. In terms of the fishing gear, the fishermen were unable to fish for anywhere from 0 to 3 days after the cyclone due to the weather conditions, and there were fairly limited reports of their lost gear, but that was very shortly after the cyclone, and we have these follow-up surveys on assets that we're still analyzing to look at the household level on what all of the losses were on that side. In terms of the crops and property, do have some more data. So you can see here some of those. This is all mapped flooding. You can see all these little squarish rectangular things are rice fields. So they're really reliant on rice within Madagascar in general, but especially this area. And so this purple area is all satellite imagery of flooded space, which you can't really see too well. Unfortunately, the maps for the flooding don't cover all of the villages. So Kelly had a nice box on here, which I did not include, that shows the limit of the data, which is just to the northern part. So it really just covers about 1-ish sites for actual flooding data. But in terms of the reporting of what's happening on the impacts on rice, this is a picture from a reporter a reporter on the ground took of this guy digging out his rice crops. So there's a lot of silt and sand covering the rices following the event, and what was reported throughout was somewhere around 10 to 50% of both paddy rice and slash and burn rice that they conduct in the area was reported damaged or completely destroyed. So we are seeing definitely pretty extensive impacts on some of the crops. In terms of other crops that they consume here, they follow a bit of a different pattern. The bananas, there's quite a bit of damage to, but the others are all kind of similarly centered around 50% reported damaged. Then the other thing they do there beyond just food for consumption is they produce these cash crops, which supply a lot of income. So there's vanilla and cloves. These ones experienced a little bit less of the damage from flooding and wind. And so we're looking into how that is impacting the income generation in those communities. We also know that there were a lot of houses and other forms of assets that were lost, and so some of the shift in income has to go to rebuilding. So this is a picture that Chris took of one of the houses that was destroyed during the storm, so we're working on understanding that. So how do the changes, though, in the ecological and fishing gear come together to affect catch? I just have today the village level catch data, but I do have individual fishermen level data that I'm working on, but the fishermen all have different names, and so figuring out who's who is still an issue of data cleaning. But you see here, and this data only goes up, unfortunately, to April. But there is this drop off, and it does seem like that gets maintained for a little while. So I'm still working on cleaning that data that extends beyond that. So you do have a pretty variable system, and it does seem like there is a drop off, at least for a month or so following the cyclone event. The other thing is that anecdotally we know that folks may change some of their fishing behavior. So this picture, again, by a reporter on the ground, had people taking their nets out into some of the flooded rice fields to catch fish. And so I'm working to get the data on individual fishing behavior to understand changes in gear types, changes in target species, changes in fishing location, and ultimately that fishing consumption piece. These two come together to look at the impacts on income, and as I mentioned, I don't have the household data available yet, but I do have the data on changes in price. And so following the cyclone, there's this increase from anywhere from 10 to 30% in these staple goods in prices across these villages. And what this means is that even without knowing that there are the decreases in income, we know that the same income can really buy less within these villages for all the way up to about 8 months following that cyclone event. When this all comes together to look at nutrition, I'm doing that at the household level, but still working on that. The rapid version, though, for understanding impacts on nutrition is the Coping Strategy Index. So this was developed to look at a quick food security monitoring and assessment. It measures behavioral responses to food insecurity. Each of these questions is focused on how many days of the last week did you engage in one of these kinds of activities. These are just a few examples of those. But what we can see is there are questions like, how many days did you skip an entire day without eating? So not many skipped entire days without eating. However, there's starting to be more who reduced the number of meals eaten in a day or restricted consumption by non-workers, many people limiting portion size, and many people relying on these less preferred or less expensive foods. There are also other kinds of food production behaviors that you can engage in. So many more people harvesting these immature crops, a few people who started hunting when they hadn't been, and then other people who are gathering some different kinds of wild foods to supplement within the diet. So those come together to form the Coping Strategy Index with a couple other questions. And that gives some insight, at least in terms of the immediate change within those villages, in the immediate behavioral responses at least. So I'll shift scales now to move from looking at those local consequences to the much more global consequences of impacts of a red tide event from salmon trade in Chile. So as I mentioned, these changes in trade from one country at the national level implies these distant impacts within the trade network. And this is really of interest within the seafood context. I mentioned earlier that seafood is becoming increasingly globalized. So here's some data from work that I've done looking at the increasing or near doubling of seafood trade from the mid-90s to 2012, as well as increasing connectivity in the network. So countries are having around 65% more trade partners from the mid-90s to 2012. So you have this increasing trade and increasing connectivity within the global network of seafood trade. This happens for a variety of reasons. There are a number of advantages to participating in global trade. So you have access to larger markets and more capital investment. You have access to a greater diversity of products. It's largely driven by this decreasing transportation and communication costs that enable us to get these benefits. And it also allows particular regions to overcome supply shocks. So if there's a decrease in available foods in one place, they can now access those foods from elsewhere. But this comes with a number of disadvantages. So one, of course, that's come to our attention, that's in the news pretty often, is the loss of particular sectors' jobs when you're engaging in trade. Relying on other countries, especially for your food resources, can be politically undesirable. And then finally, there's the exposure to these external shocks. So if there's a disruption in one part of the world, that may be propagated through the trade network and end up affecting the food that you actually have within your country. So it's this exposure to these external shocks that I'm really focusing on in this case. I've done some work in this area before, so one working with a model for modeling the network impacts of seafood trade, as well as shocks within the grain network with Philippe and a group here at SESYNC. So this is a little GIF of one of these shocks spreading throughout the grain trade network, showing the supply decrease in red accumulating in certain countries and how those change the imports and exports. In general, what's been found by these kinds of simple network models is that net importers, developing countries, and countries with low food stocks tend to be more exposed to these kinds of shock events. But since there isn't very much empirical evidence, we haven't observed how these shocks actually move through these networks, it's hard for us to actually validate these models, first of all, or second of all, understand how quickly the networks rebound or what kinds of novel risks may be arising from this increasing connectivity in our food networks. So one way to do this is by picking a particular case study that's happened recently because there's only been monthly trade data since 2014, and look at what actually happened in terms of, and track the changes in trade flows through the trade network. So the case that have been focusing on is a red tide event that occurred in last spring, or not last spring, 2 springs ago, 2016. And this is a globally important species, Chile. So there's good data on salmon globally, and Chile is a top producer of salmon. So this red tide event occurred and killed both local fish as well as lots of the salmon, affecting about 20% of the salmon production. The approach that I'm taking here is really kind of a mixed methods or multiple lines of evidence approach to understanding the shock event. When it comes to these global events, you want to avoid trying to model the whole world, but also you need to avoid bias of only looking in certain places for the impacts. So one way that I'm doing this is bringing in these multiple lines of evidence. So the first piece is understanding some of the context of the shock event itself to understand where we might expect to see the effects and what the timeline was of the particular case. So one important piece of information with this context, within the context of Chile, is that there were a lot of protests in response to this red tide event. The salmon farmers had been being blamed by the local fishermen for dumping the dead salmon into the water and causing the red tide event itself. And then the salmon industry is saying, no, it was the strong El Nino event. Either way, this led to a number of protests and the blocking of Chiloé Island, where a lot of the salmon was being produced. And this sort of adds to the timeline of when we would expect to see the salmon event, to salmon shock event, to extend to, with this additional political response on top of the environmental component. The second layer is to think about the neighborhood impacts. So what were the changes to trade to the immediate trade partners of Chile? You can see this by looking at the exports from Chile to its trade partners. This stacked line graph has each of the different major trading partners with Chile over time from May 2014. In this dashed box here, this is the red tide event. You see that the exports out of Chile reached about half of what they previously had been, or a little below that, and the distribution, though, of decrease to exports to those countries can be looked at one way by using an intervention model. So these are kind of preliminary results, but what I did was I fit an ARIMA intervention model. So this is an autoregressive model that takes into account the time series component, but allows you to fit a different mean for before the shock and after the shock. So you can look at the change before and after the shock while taking into account the time series pattern. So overall, the shock event led to about 100,000 ton decrease in exports. About a third of that went to the Philippines, a third to the United States, and a third to Canada, with everyone else falling a little bit less. And the Philippines here is really important because they're a major processor of salmon. So that right there really suggests that you have these knock-on effects of changes in trade, since the Philippines isn't eating all that salmon. to understand the timing component and some of the implied global impacts, I look at global prices. So you have the global price index plotted here on that same figure, but in black. And you'll see it starts climbing during that red tide event, and it really reaches its peak about 6 months later before dropping back off. It spikes again a second time in the following winter, and that's a separate event. But in case you're curious, there was a big sea lice outbreak in Norway that killed a lot of Norway's salmon production, and they're actually the #1 producer of salmon in the world. And so this suggests, though, that it's this time period of about 6 months after that you would expect the market to be sort of readjusting and that shock to be moving through that trade network. So the final piece is really the most important piece in my opinion, which is understanding the changes in trade flows actually over time. So get that time series of networks and trace changes in trade flows throughout the whole network, not just to the immediate trade partners. And the way that I'm trying to estimate these more global impacts and understand those dynamics is by adapting a method called synthetic control. So this comes from out of econometrics, and what it does, so if you just think of a time series for one site, so not the network context, but if you have some kind of time series and a shock event, say here in yellow, you essentially want to know what's the difference between that and what would have happened without the shock event. So maybe if it would have looked like that, this would be the difference, and you'd say that's the impact of the shock. Alternatively, though, what if the time series after that shock event had looked more like that? Well, that gives you a really different estimate in what the impact of that shock is. And so what we have to do is try to create this unobservable counterfactual. So figure out what would our time series have looked like had we not had that shock event. What Abidi has developed is he takes some kind of affected, so some sort of treated site, so here you have A, and say that's where the shock event happened. But you also know there's B, C, and D, which were unaffected by that shock event. So we have all their time series. The idea is that you use the time series before the shock of B, C, and D, and use a weighted linear combination of those to create as close as possible the pattern before that shock event and keep those weightings after it to represent your synthetic A. So you create this sort of other world by a combination of these others. The idea being that they're capturing together, capturing some of the fundamental properties of what was going on within the system. And so I've been working on trying to extend that approach within the network context, and also been looking at some nonlinear approaches, one called convergent cross-mapping that I've been working on with Juan Roca, who spoke here last spring, I think. And so trying to get this into the network context. How's it going so far? Really horribly. So these are all of the points, and this regression of it looks terrible. But there are some really promising approaches. So one is I have more recent data with more resolution on the commodity codes. So these are pretty aggregated. Those aggregated commodity codes just aren't going to give you as much variability to try to fit with. And yeah, and then of course just checking some of the data cleaning and code cleaning. But the other thing is maybe trying to resolve this big Germany-Poland flow. So this is the network here. You can't see the countries that well, but this gigantic band here is between Germany and Poland. So because of some of the changes in the way that the imports rules happen, there's a lot of processing going on in Poland. And because of that, you get this gigantic flow between them, which is a problem because I think too much of the network's trying to accommodate fitting what's going on there, and it's driving other things to not look quite right. So anyway, working on trying to resolve that within this network context. But to sort of bring this back together, I think that both of these approaches of understanding what's happening on the ground to get to the food security part and how they're responding to understand resilience and measures or sort of validate some of those resilience metric is really important for understanding these environmental shocks. But similarly, looking across the globe to understand these much broader impacts and some of the maybe novel risks that are happening from increasing globalization of our food commodities is important because these contribute to two very different but related components, I think, of the resilience of the food system overall. And going forward, I'd like to build on some of these case studies so that way I can try to come up with something that's more generalizable, not single local cases or single global cases, so that we can move to some of these general to get more generalizable findings about resilience within these food systems. So with that, I'd like to acknowledge some of the various funding sources and, of course, all of the people who've been involved in these projects along the way. And I'd be happy to take any